We'll be discussing transshipment and total logistics cost. Total logistics cost is the means by which we can make a lot of decisions with respect to what is the best logistics network design, in particular what type of transshipment is most effective. We're going to start with an example, example A. This is a full truckload example that illustrates the combination of location and freight transport. What is key is that for full truckloads, we can basically just focus on minimizing transportation cost and do not need to consider inventory cost because the size of the shipment has already been determined to be the maximum payload that is able to be carried by the truckloads. So this is an example, the same one that is covered in the slides. Here we're defining the unit weight for the two suppliers that are distributing two different products to a distribution center, and then from the distribution center they'll be aggregated and shipped as full truckloads to 3 customers. So we have the weights in pounds of the two products, we have the cubic volume, and then we have the annual demand, and this is in tons per year. And notice that I've included a capital S, and the reason is that to refer to the suppliers. I'll also be using a capital C to refer to the customers, or alternatively you can think of the S as being inbound versus the C as outbound. So these are the two annual demands, and then from this we can calculate the density of the shipment. And what I'm going to do is create a shipment structure, and again I'm using the capital S to indicate that these are the inbound shipments from the two suppliers. And I'm going to use the MATLOG function called vec_destruct, and what it does is it allows us to specify a name for the fields together with a vector representing the values, and then as a result it'll create a array of structures. In this case we'll have a 2-element array of structures corresponding to the two suppliers. And then for the customers, the information that we know for the 3 customers is what percent of the total demand of the 2 products do they receive, and we can assume that they're getting equal percentages of the 2 products. So sort of a latent or unspecified assumption is that the 2 products are received in the same proportion. So we can define this percent vector, and then what I'm going to do here is use the MATLOG function agship to do all of the aggregation of density, adding up the demands and so on. So it's a convenient way as opposed to using the formulas. And I'm going to create just a single structure, and notice that's different than the structure created for the suppliers. And then what I'm going to do here is expand that shipment structure and include the first 2 elements for the inbound supplier shipment structures, and then I'm going to call again the vec_destruct, and then do like I did up here, create the corresponding demand F, and I'm going to do that by taking the demand for the aggregate, which is the sum of the 2 individual demands. It's a total of 480 tons, and then multiplying that times the percentages gives the percentage in tons of the aggregate product for the 3 customers. And here I'm using vec_destruct. Here I didn't include a shipment structure because I was starting from scratch. And what I'm going to do here is take this aggregate shipment and essentially replace the single shipment structure with a 3-element shipment array. And then here I'm appending the 2. So when I finish all of this, and then I call the structure display or sDisplay function, I get now a total of 5 shipments, 2 inbound and 3 outbound. And for each of those I have the demand and the densities. And then for the truck I'm going to do a similar thing. Instead of using vec_destruct, I'm just using the struct function, and the reason is that each of the 3 elements for the 3 fields of the truck structure are just scalars, so I don't need to create multiple arrays of truck structures. So I can do that in one step. And then I can use the max payload function in MATLOG to take the structure and the for the shipments and for the truck, and determine a total of 5 maximum payloads, 1 for each of the shipments. And notice that the last 3 are identical. because they're all shipping. You can think of it as a single aggregate outbound shipment that is composed of the two inbound shipments. And then here I'm specifying the I-40 coordinates for the suppliers and for the customers. And then I can locate the distribution center, assuming to try to minimize transport cost, and that's because of the full truckload assumption. And I can do that by defining first the number or frequency of shipments, which is just F divided by Qmax. And then I can multiply that times the transport rate in dollars per mile to get my monetary weight in dollars per mile. And then I can call mini-sum location to get the coordinate of 150, which corresponds to Statesville as the optimal location. Alternatively, I could define a function handle and then call fminsearch and take as a starting point the mean of all of the suppliers and customers, and I get the same result. And then an extension of this problem is to consider a frequency constraint that we have to have at least monthly shipments. So looking at the way of handling this constraint, I can start off. First, I can look at what was the constraint previously. And the constraint is only for the outbound shipments. But in fact, the two suppliers are greater than 12, so it would not come into play otherwise. But for the three outbound, the first two are below the 12, so these need to be at least 12, and only the third customer is above the threshold. So the way we can handle that is first define what is the minimum number of shipments, which is just 1 over the interval constraint. And then I'm going to keep the original n values, and then I'm going to take the maximum of either the existing or this minimum number to get a new vector, and now I have the 12s replacing the values that were less than 12. I can recalculate my monetary weights and then resolve the problem. And I get a solution for 190, which in this example then corresponds to Winston-Salem. So the fact of the frequency constraint resulted in a change in the optimal location. We can continue to extend this example beyond what was actually talked about in class in terms of the slide description. And if, for example, we knew the value of the shipments, then we could look at things other than assuming just full truckload shipment. We can actually use the total logistics cost as something we can use to determine what is the optimal location. So to do that, I'm going to define the value of each unit in terms of dollar per unit. And then for this, we need to define alpha. And in this case, I'm going to assume that at both suppliers, there's batch production. So essentially zero inventory held at the origin. And then I'm going to assume that at the distribution center that we're building, we're doing uncoordinated shipments. So we're just optimizing the inbound and outbound shipments separately, not trying to coordinate them and do some type of cross-docking. And then also we're going to assume that there is constant consumption at the customer locations. So with all of those assumptions, we can assume that our alpha values are going to be 0.5 both for the inbound and for the outbound. 0.5 on the inbound because of the uncoordinated distribution center, 0 at the origin on the inbound, and then for the outbound, a 0 at the origin, which is the distribution center, and then 0.5 at the destination, which is the customer, because of the constant consumption assumption that we're making. So with this alpha 0.5, that's going to be used for all of our shipments. And then the other thing we need to do is to determine the value V on a basis of dollar per ton. So the dollar per unit value can be converted to dollar per ton by taking the unit weight divided by 2,000. We're going to take 0.3 as our default H value. And again, because nothing in the problem specified a value, that's probably a reasonable default value. If we had information in terms of obsolescence, then we would be able to refine that to a more accurate estimate. And then for the shipment structure here, I'm going to take the inbound shipment structure, which I still have as my SH with a capital S, and define this as a new aggregate shipment, and then redefine my shipment structure just like I did before by multiplying times the percentage and applying this. And now I have again 5 shipments, and the additional information is I have the alpha, I have the value in terms of dollar per ton. Again, it's the same for the outbound because you can think of it as shipping a single aggregate shipment, and then the H values are 0.3 for both for all of the shipments. So with that information, we could solve the problem. One of the things that we don't have in terms of this problem is a means of specifying what is the distance in terms of being able to solve it as a problem that tries to change the location to determine which one minimizes the total logistics cost. So we can include that information by doing the calculation for a given location X. Again, this is a single dimension along I-40, and we're going to define our shipment distance function handle. We're going to use the vec_destruct function in our function handle, and we're going to pass it our shipment structure. And then every time we call this function handle, it's going to essentially create new distance values, and it's going to do that by using the distance function and getting the distance from the 2 suppliers to whatever location X, and then also taking the distance from location X to our 3 customers, and in this case multiplying all of this times 1.2. In general, if we know we're doing along I-40, the distances are probably closer to a straight line, but in general we're using 0.2 as their security factor. So I can define this function handle. And so basically what we have now is a means of, given an X value, we can update our shipment structure. Now we can determine the total logistics cost with full truckload. We're assuming full truckload still used for all transport. And what is the then corresponding total logistics cost? With that, we can define the total logistics cost using the matlog function, total log cost, together with the transport charge. And then here what we're doing is we're taking the distance handle for shipments and taking the current location X and then redefining what the shipment structure is. So every time we call the trans charge with a different X value, we're getting a different shipment structure, which then gives us a different transportation charge, which then gives us a different total logistics cost for each of the entities, and then we're summing all of that up. So this one function handle is doing a lot of work in calculating the total logistics cost, and we can then determine what is our total logistics cost for our distribution center at Winston-Salem, and that value is 1.2 to the 5th power as our full truckload. And that's where we're trying to minimize just the transportation cost. If instead we want to minimize total logistics cost and not use a full truckload assumption, we can call fminsearch with the same function handle. And now we get a result, and if we look at this result, we can plot it. And now we get, and we can see it's really sort of an interesting result. We get an overall decreasing result. Looking at this, it still is the case that we have a minimum, and this is at 150, which is Statesville. We also have a minimum here, but it's a local minima at the 190, and probably the second best location is sort of in between Statesville and Winston-Salem. So when we're dealing with total logistics cost, it's not the case that we have a piecewise linear objective function. In this case, we could have a situation where we could get a solution that's not at one of the existing locations, even in one dimension. And one of the problems we have is that we have a very small minimum at this point, but it's basically inside of a hole. And the reason for that is that the transportation charge function includes a minimum charge calculation. So we're incurring that minimum charge even when we're 1 mile away from the location, and not until we reach exactly that location do we drop into this hole. So essentially this hole, it looks probably a little bit wider than it is, only because of the resolution of the plotting function. But in essence, it's sort of like in calculus and approaching infinity. It approaches being almost connected together, and only right at the location as we approach zero distance do we drop into this hole. And at the bottom of this hole, that corresponds to the case where we do actually have zero distance, in this case to the 150 Statesville location. But everywhere else we still have a positive distance. So that's one of the difficulties and the real problem of dealing with this minimum charge phenomena. So a means of handling it then would be to basically, so we can extend this problem. Instead of assuming that we're shipping full truckload, we can try to get a better cost by actually calling the min TLC function using our same function handle. So instead of making the full truckload assumption, we're actually going to use the min TLC function to determine what is the best shipment size and then return the corresponding total logistics cost. So we can define another function handle that is just trying to minimize total logistics cost. And in this case, the size of the shipment is changing. So we can do like we did before, call fmin search. And now we get a different result. And now we have a value, and in this case, the blue line is well below because I have hold on, this previous line is still there in the plot. And you can see that there's been quite a substantial drop in the total logistics cost by including the ability to change the quantity shipped. And here you see an even more exaggerated version of the minimum charge phenomena. In this case, as we get closer, the size of the shipment can't go immediately down to zero for this one. So as a result of the minimum charge, we end up having a steep slope up to the top of this point, and then we kind of drop into this. So this is literally almost like a needle in a haystack. So in terms of an optimization procedure, being able to actually find this, there's probably no way of getting inside and finding this minima unless you actually start at the existing facilities as a starting point. Overall, the best that the nonlinear optimization could do, and essentially the Nelder-Mead would essentially just overlook some of these sort of narrow basins and just move to the minimum, and it found a point right here, which is the 168 mile marker. And for this overall function, ignoring these little wells, that is indeed the overall minimum. But for this particular problem, we could see that at Statesville, the total logistics cost is 7.1. And when we do a comparison of the full truckload to the optimal total logistics cost, we get a difference of over 77% higher for the full truckload, as opposed to locating at the minimum for this example, which is in Statesville. So essentially, in terms of being able to solve this, we'd want to use fmin search together with probably looking at all of the existing facilities as additional locations. And the reason being is because of the minimum charge. The next example, example B, is an example of the difference between using direct shipments from suppliers to customer or using transshipment at a distribution center, and looking at what is the best alternative. And in general, there's not a single always best solution. It could be that direct shipment is better or transshipment is better at a distribution center, and using total logistics cost is a means of being able to assess which is the better alternative. So to do this, for this example, we're going to have 4 customers located in 4 different cities around the country, and 3 suppliers, again located in this case, 3 different cities. We're going to use city to long lat to do the determination of the longitude latitude for both elements. And then we're going to consider 3 different products. So again, we're going to be doing a calculation similar to before, so I'm just going to quickly go through this. We're defining the PPI values for both truckload and LTL. The reason for LTL is for transshipment. When you're using a distribution center, you typically don't use LTL. But for the direct shipments, if you have high value product that is, shipped in small quantities, it can well be the case that LTL is the way to go for the direct shipments. And we're going to do like we did before, defining the demand and density. For this one, we're going to assume batch production at the supplier, constant consumption at the customers. So I'm going to define different alphas for S and C in this case. And the reason is I want to also consider the possibility of using coordination, in particular cross-docking. So in the previous example, I had 0.5 for everything because I was assuming uncoordinated. Here I want to make the alpha for the supplier refer to just at the origin where the product is produced. We're doing batch production, so it should be 0. And then I can change the alphas for the distribution center depending on whether or not I'm doing uncoordinated, which I'd want to include 0.5 for the inbound, or if I'm doing cross-docking, then I have 0 at the distribution center. So I'm going to keep it 0 in this case initially. And then I'm going to take the percentages and define these volumes. So again, this is similar to the previous example, so I'm not going to spend a lot of time talking about it. Here at this step, what I'm doing is creating a series of matrices. And the reason is that when I create these matrices, I can then, when I'm using the vec_destruct function, I can take the entire matrix and squeeze it into a single column vector. And that's a nice convenient way of handling the case where I have 2 different levels of a logistics network. And I can create the overall matrix that represents all of the lanes connecting one level to another. In this case, it would be a 3x4 matrix. And when I squeeze it down, I end up with 12 shipments that correspond to all the possible connections from each supplier to each of the 4 customers. So I have 3 suppliers and 4 customers, so it's 3 times 4, or 12 total connections. Here I'm defining a distance matrix. So for direct shipments, I'm not locating the distribution center, so I don't need to make it a variable. I can predefine my distances, and here I'm just defining the distance field directly and then squeezing the distance matrix into a column vector. So I can do all of this as one step. And here are the 12 shipments that have been created. And these are the direct shipment distances from each supplier to the corresponding customers. I can determine what is the optimal shipment size for all 12 of these shipments by calling the min_TLC function. And here I'm going to first call that, get the min_TLC for all 12 of those. Here I can define, because I want to know what the maximum payload is for that particular shipment. Again, it's going to differ because they have different densities. N1 means the frequency for these independent shipments. This is the number of days between shipments. And then I can use vDisplay to display all of this. So it gives me all this information about all the shipments. It tells me the optimal quantity being shipped, the total logistics cost. It also adds up the total logistics cost for all 12 of these shipments. So I can do that I can use this direct shipment as a baseline to compare the different transshipment alternatives using a distribution center. So so one option using true is to get a total. Another option is to get an average, and both are useful. These are the optimal shipment sizes, maximum payload, frequency, interval, and then the 1 here represents direct shipments that are shipped LTL. So in this case, a total of 4 of the 12 are shipped LTL. So the first example is to use an existing distribution center In this case, I'm going to take Memphis, Tennessee as where my distribution center is located. And again, I'm using cities in this example because I'm dealing with, in this case, specific facilities, both the suppliers and the customers. So we're not dealing with any type of aggregate demand where I'd want to probably not use a city to represent an aggregate demand. So I can define the longitude, latitude of the distribution center in Memphis. And then first thing I'm going to do is plot everything. And I end up with an example showing all the different entities. Here I've separated suppliers, my distribution center in Memphis, and the 4 customers. So I've plotted all their locations. This is 1, 2, and 3 suppliers, and then the 4 customers, Milwaukee, Denver, Portland, and Tucson. And then I have a distribution center in Memphis. First, I'm going to create shipments including the distribution center. So my 12 shipments are all for direct shipment. First, think for a moment, how many shipments would I have when I have a distribution center? Well, instead of 12, I basically just have 3 shipments from the 3 suppliers to the distribution center, and then 4 outbound shipments from the distribution center to the 4 customers. So I have a total of 7 shipments using a distribution center. And here I'm going to look at first the case of no coordination. So what I want to do is take the supplier alpha, which is 0 in this case because of batch production. If I was doing constant production, this would be 0.5, and then I'm adding 0.5 for the no coordination. To get here, I'm going to define it as my alpha for my origin. And then my destination alpha is going to be 0, and then the customer alpha, which is 0.5. And then with that, I can define first a set of my 3 supplier shipments. And again, since I know the location of my distribution center, I can directly calculate the distances. Then I can do a similar thing for my outbound. In this case, for my outbound, I'm going to take my 3 supplier shipments, and as I'm creating my vector structure, I'm going to call aggregate shipment directly. And what aggregate shipment does is give me a single aggregate shipment, and then in this case, I'm overriding some of the values that are going to be different because it's an aggregate shipment. And in this case, one of the things that's different is instead of a single aggregate shipment, I'm going to use the percentages to take the overall sum of tons being shipped into the DC and spread it out over the 4 customers. For the alpha, I'm just going to be using my destination alpha, and then my distances are going to be the distances from the DC to the 3 customers. And then I'm going to combine both of these together. Each of these are arrays of 3 and 4 elements respectively, so I can use the square brackets to turn it into a single. I can also include the max payload, and then here are my 7 total shipments. And again, for the values for the outbound, they all have the same density, the same value, and the reason being is that they're aggregate shipments of the 3 different products. I could then use min-TLC to determine for both the inbound and outbound what are the optimal shipment sizes. And here I'm looking at the possibility of both truckload and LTL. The frequency, the interval, and then I can use vDisplay. And here I get the results. And for these 7 shipments, using Memphis as the DC and no coordination, turns out all of them are shipped truckload, so nobody is LTL. These are all false or 0. These are the quantities. This is the corresponding Qmaxes. And in terms of this result, 797, if I go back up here, I got 783. So just based on having a DC in Memphis with no coordination, you would be better off actually doing direct shipments. So this is a way of assessing using total logistics cost that in this case, it's actually better to have direct shipment. The next example is to use a distribution center with perfect cross-docking. So to do perfect cross-docking, we're going to be modifying the supplier alphas. Instead of having 0.5, we're going to make it 0. So these are the inbound alphas. So this, and the alpha for the supplier is 0. So everything overall is 0 in this situation. So the only thing that really changes is the alpha in the shipment structure. And then I'm going to recreate my overall shipment structure since I changed the alphas on the inbound. The outbound stay the same, so I can just use the previous customer shipments. Then I can, in this case, since I want to determine an optimal shipment interval, in this case I want to take the formulation of total logistics cost as a function of total logistics shipment interval time. So I would recommend looking at the reference on TLC with transshipment, and you can see that it reformulates total logistics cost where instead of the quantity Q, it's a function instead of the shipment interval T. And with that formulation, the function can then determine what is the optimal interval that minimizes total logistics cost. And that would then become the interval at which the inbound and outbound shipments are sequenced or coordinated for cross-docking. So when something comes in and leaves, you have to have the same shipment interval to allow cross-docking. If they're not the same, then you end up having inventory being stored at the distribution center. The extreme example of that would be no coordination, where you're not taking any coordination into account. In practice, most distribution centers would be a mix of cross-docking and no coordination. So you would take all of the different shipments and determine for each shipment, should this be cross-docked or should it just be stored with no coordination? And there are different factors that would lead to different sets of shipments being cross-docked versus having no coordination. So what I'm doing here is I'm taking total logistics cost, and the first argument should be a quantity. So I'm taking the time T, which is my variable argument, times the demands for each shipment. So that creates a Q value in this function handle. Likewise, for the trans charge, I'm doing a similar thing to get a Q value in terms of T, the shipment interval. Everything else stays the same for this function handle. And then here I'm adding using the IFF function, I'm adding a capability to this function handle. And the reason is that otherwise I end up with results that are not feasible, that exceed Qmax. So I can use my calculated Qmax value inside of my function handle. That's why I calculated it up here. And what I want to do is, as long as the quantity I'm using, which is derived from the interval T, is less than Qmax, I use the total logistics cost. Otherwise, I set it equal to infinity. So that'll keep the quantity when I'm optimizing from going beyond Qmax. And in terms of function handle, I put a 0 here to indicate my base calculation. And then I've left the 0 out. The 3 corresponds to the example. So this is the ultimate function handle that I'll be using that uses IFF. And then as a starting point, I'm just taking the minimum of the Qmax over T, and that gives me a starting time. And then using that starting time, I'm taking the sum of all of the total logistics cost and trying to minimize that. And I end up with a value of 0.05 years as the optimal shipment result. I can take all of that, and here I'm going to first convert the optimal shipment interval times into quantities. And then I'm going to call trans charge with those quantities. And here all I'm interested in is whether or not it was a less than truckload shipment. So I'm ignoring the first output argument, which is the actual charge value. And then I can convert and determine the total logistics cost using that optimal interval. Likewise, I can calculate the number of shipments and the frequency, and then finally I can display all of this. And when everything is done, it turns out that, again, nothing is shipped to LTL, but here my total logistics cost is reduced to 634 as compared to 797. So in this case, it looks like doing perfect cross-docking is better than no coordination in a DC and direct shipment. We could actually do probably better than this by actually first, one possibility would be to determine a different location for the distribution center. And then secondly, which we're not going to cover in this example, would be to try to do some shipments with cross-docking and some of the shipments as no coordination. And that would correspond to more realistic what actually happens at most distribution centers. So the final example is I'm going to use the initial starting point as the optimal location found using full truckload approximation. I just basically need a starting point, so I'm going to call F a mini sum location. In this case, take Tulsa, Oklahoma as a starting point, and now with that starting point, I can determine an optimal shipment size as a subroutine in the location procedure. So in this case, I'm going to determine an optimal DC, assuming no coordination. So like before, here I'm going to define my inbound alpha to be 0.5, and then redefine my shipment structure so it has the new alpha. So now I'm going back to what I had initially as my alpha. Everything else stays the same. Here I can define a shipment structure as a function of the distance like we did before. So and notice here that for the XY, this is a longitude latitude. So when I use it, I can't just call XY by itself, because when I'm calling fmin search and it's trying to minimize, it wouldn't know that it should have two elements. So here I have to take the XY result and explicitly separate it into longitude and latitude as two elements to be able to actually use it each time I use it in the distance function. So with that, I can define my function handle to give me a shipment structure with a distance corresponding to a particular location. Then I can use that in fmin search. And then with my starting point, I can call that fmin search. Here I get a result to see what the corresponding location is. Turns out to be Aurora, Colorado as the optimal. And I can report the result. And I up with 754, which is not as good as the perfect cross-docking. I can then do the same thing, determine the optimal DC location with perfect cross-docking. Again, I'm going to change the alphas. And here I'm going to define distance like I did before. And then the total logistics cost is going to be defined in terms of the shipment interval, the optimal shipment interval, that I can call fmin search, get my result. Here I get Wichita, Kansas. I can report the result, and I get 598. So this is actually the lowest value overall. Finally, for this example, I'm going to report all of the results. And this kind of summarizes everything we found. These are the total logistics cost for all of these options. For direct shipment, we have 4 that are shipped LTL of the 12. These are the total logistics cost. The best overall is to do perfect cross-docking. That just means that all of the shipments, inbound and outbound, are cross-docked. Less than perfect would be where you have a mix of uncoordinated and only some that are cross-docked. So this is our best result. This gives the time in days between shipments. And that is an analysis of this problem. The last example that we'll be talking about is the example where we had for Lowe's Home Improvement to basically try to do a mix of top-down and bottom-up analysis. Ultimately, what this is an example of is how to do logistics network design using total logistics cost. Previously, we did some problems where we were basically doing network design, like in the case of Popco, where we were using full truckload. And in this case, we're going to be still continuing with the full truckload, but we're going to try to determine the optimal number of DCs based on trying to minimize total logistics cost, as opposed to having specific information about production cost at each facility. So in contrast to the Popco example, where we use linear regression together with the production cost at each plant to estimate what would be the fixed cost In that case, we could then use the UFL heuristic to determine the optimal number. Well, in this case, we're going to be using just total logistics cost and not any explicit notion of individual fixed cost for each facility. In this case, the number of facilities is going to be determined using the ALA procedure, and we're going to look at different numbers of distribution centers, and then what is the overall corresponding total logistics cost. And that total logistics cost is just a function of, in this case, nothing to do with production. So the reason that this is appropriate for Lowe's is that at their distribution center, they're doing essentially no actual production of the product. So it could be the case that there are essentially no real fixed cost at the distribution center. The way that the fixed costs come into play is our assumption that we're using full truckload. In the case of full truckload, there's a certain minimum size that's required to make it cost effective for the transportation component. And that is what dictates not having an infinite number of distribution centers to be able to best utilize the full truckload. So it's an alternate means of doing logistics network design without requiring an actual explicit fixed cost. And it would be appropriate in cases where you're dealing primarily with distribution centers as opposed to any type of manufacturing facility as your primary means. So for this example, we're going to be using continental US data, and it's going to be 3-digit zip codes with populations of at least 100,000. The reason is that in this example, I'm using the 3-digit zip codes to represent all of my suppliers in addition to stores. So I'm going to assume I have several stores. So it's not one store, but probably several stores at each 3-digit zip. But also I'm assuming that we have several suppliers located in each 3-digit zip that actually ship to all of the distribution centers. And in terms of shipments, we're going to assume full truckload shipments for all of the suppliers that are in a 3-digit zip. What that means is that if there's, say, 3 or 4 suppliers in one 3-digit zip, we're assuming that they coordinate together and share truckloads so that all of their products are shipped as aggregate shipments from that 3-digit zip to the distribution centers located all over the country. We're not assuming that each supplier individually is shipping full truckload. And I think for most distribution networks, that's probably a fairly reasonable assumption. It wouldn't make sense, unless you're dealing with really high value or high volume product from a supplier, that you'd be maybe directly shipping full truckloads. More likely you'd be combining with others. And nowadays with transportation management systems, it's not unrealistic to assume that all of the suppliers' inbound shipments to a distribution center would be coordinated in such a manner. So we're going to assume that. So we're going to take this as our set of customer and supplier locations. So I'm taking the CXYs and also saying these are going to be my supplier locations. Again, not individual suppliers, but in this sense it's an aggregate of all the suppliers. I'm not going to be using the area approximation because I don't think the numbers of suppliers in the 3-digit zip are significant. This is a 2017 cost of goods sold. So that's my top-down piece of data. Everything else is going to be, I guess the other top-down would be the average value. In this case, I'm going to use $7,000 per ton. That's the average value for LTL shipments. And then with that, I can estimate the annual demand as just COGS divided by the average shipment value. So in this case, I get the total demand in tons for the product. And then I'm going to use average density of a class 100 product as my average density. I'm going to assume batch production at all the suppliers. Typically they'd be supplying for Lowe's, Walmart, probably several other companies. So they wouldn't be dedicated just for Lowe's. I'm going to assume uncoordinated DC and constant consumption at the stores, a 0.3 H value, and then the most recent truckload PPI value. So with that, I'm going to create an allocation handle for ALA and also a inventory cost handle. I'm going to create my truck structure using the most recent PPI value for truckload, using the normal constants. Here I can create a max payload, and that'll be used for all of the full truckload shipments. And then for the demand, I'm going to assume it's proportional to the population of the 3-digit zip. So I'm taking pop divided by the sum of pop to get a weighted average, and then taking the demand F and expanding it. And then for the suppliers, I'm going to assume that there's an equal allocation of supply. And that, another assumption is you could do the suppliers based on population, but I'm assuming that there's not a correlation between population and suppliers, except for the fact that we're limiting ourselves to populations of at least 100,000. I think the reason is that Lowe's and a lot of big chain retailers have a lot of suppliers that are located in fairly small towns, and probably relatively few that are in really large towns because of the high cost of labor and land and real estate. So I think in terms of supply chain for a company like Lowe's, it's probably not exactly proportional to population. Again, that's something that could be verified. I'm just going to make that as a reasonable guess. And then I'm going to define my cost handle for distances, not doing any type of area adjustment. And the reason for the store locations that I'm not going to do area adjustment is, again, the number, even in a 3-digit zip, is probably in the order of a dozen or so. So it really doesn't actually require it. And then also, I'm not using UFL, I'm using the ALA procedure. And it's unlikely that I'm going to be locating right at one of the locations. Again, because there's no notion of fixed cost associated with this. That could be saved by locating right at a store location. Then I'm creating my demand for my customers, my demand for the suppliers, and then this is my overall W matrix as a product of demand and my transport rate for full truckload. And I can define a function handle. Again, it's just going to be the product of W times D. And then an allocation handle. So with all of that, I can calculate the inventory cost, and that's going to be the supplier to DC, and then the DC to store, using the corresponding alpha values. And I'm assuming the inventory cost is basically, a product of alpha VH times the maximum Qmax, and then it's times the number of suppliers times the number of DCs, which is what I get here, plus the number of stores, which is the length of my FC. So now I have a function handle that gives me inventory cost, and then I can solve it using the ALA procedure, using this allocation handle. And I'm going to assume a maximum of 20 distribution centers. I'm going to define a starting seed. I'm going to clear this, and what I'm creating here is a vector of results for each store. Then I'm going to use that vector to determine what is the optimal point. I'm going to start off with a total logistics cost of infinity, and then I'm going to start printing results, and then I'm going to call the ALA procedure with this allocation handle. And then this is the basic logic. The only thing I'm including here is, in addition to the call to ALA, which returns the transport cost as the only objective function value, I'm then calling my inventory cost handle with that particular location for the distribution centers and getting the corresponding inventory cost. And then I'm adding both of those together to get the total logistics cost. And then that's what I use to determine, should I continue going through the loop? Am I getting a decrease in total value? And for each of these, I'm doing a total of 5 runs through the procedure. And I'm doing this, I'm not doing a while loop, so I'm going to basically execute all of these because they're for loops as opposed to while loops. Let me go ahead and run that. You can see it's taking a while because I'm actually plotting all of this because I had a plot window open. So if you want to eliminate that, I could have started, if I had not started with a figure open, it wouldn't be doing this plot. What I'm going to do is actually kill the figure. And you can see it'll speed up the calculations tremendously. It was spending most of its time doing the plotting. So now I'm up to 6. And if you're looking at this last column, we're trying to minimize that. So far 7 is a minimum, 8, 9. And then with 10, I'm starting to get an increase in total logistics cost. So for this example, it looks like 9 distribution centers would be the optimal. Here, notice 11 actually is a little bit lower than 10, but still greater than 9. And then I end up with the locations of the 9. I'm reporting just the minimum total logistics cost found. And if I want to compare, according to the Lowe's information from 2016, they have a total of 15 regional distribution centers as opposed to 9 optimal that we found. So comparing the total logistics cost for a 15 solution compared to 9, it's less than a 1% difference. So our 9 versus the 15 is within 1% in terms of total logistics cost. And that really just means that there's probably other factors not included in our model that would lead Lowe's to want to have more than 9. Within 1%, essentially there's other considerations that would probably favor having a greater number. Probably the most likely one would be responsiveness. With 15, it's more likely that distribution centers are closer to stores and can provide inventory more quickly. And that's something that our calculation of total logistics cost is not actually incorporating. Another factor could be we're not looking at any type of cross-docking. We're assuming no coordination. So finally, we can overall plot our results, and we end up with this figure. And as you can see, again, it's fairly flat in terms of total logistics cost over quite an extensive range. And only when you get to 20 is it even starting to increase. And in terms of minimums, it really starts to set in at even 5 distribution centers. So in terms of total logistics cost, it's not a very sharp tool to actually tell us exactly how many distribution centers. And again, it's just a fact. I think that there are a lot of other considerations beyond just the total logistics cost. But it does give us a way of actually capturing, I would say, the majority of the cost associated with selecting the number of distribution centers. In the case of Lowe's, because transportation cost, including the inventory cost associated with carrying the products being transported, is the major source of a lot of the cost of running the network.